So let's comment what does it mean. So it means that first we compute following thing, how to call it, function. So we compute the thing for every possible linear subspace of Cn. Cn is where our matrix A and eigenvector x are defined. This is a vector space. And we've taken like every possible subspace of size P, and then we compute a maximum value for each subspace. So we have a set of maximum values. This set is actually fine. And then we compute among, so we have a set of maximum values, and then we compute a minimum over this set. Minimum across all LP. And this is a way to use this formula. And LP is P's eigenvalue. Should probably comment from Andy. So here A is Hermitian matrix, and for Hermitian matrix all eigenvalues are positive real, and we can order them. So this formula is for so this is, if we prove it, it becomes inequality. This is for the lowest eigenvalue, and this is for the this eigenvalue. Yes. Yeah. Fine, at least on this one. Okay. So and this is a way to build an estimate. I will avoid proving it. It's actually, you can do it in a very similar way. You need to consider, you also do some kind of eigenvalue decomposition, but then you consider an I intersection of two spaces, LP, and then something like this, and this is a space built on eigenvectors something like this. Probably yeah, like this. And then you kind of consider two spaces, do some I intersection between them, and then build estimates like this. And it's more or less a standard orthogonalization procedure. If you ever did linear algebra, sometimes you need to do an orthogonalization to find all eigenvectors. But I will just avoid it, and I believe you can. If you think for a bit, you can build this proof from this proof. And what should we say for P equal 1? We have this formula. Makes sense because there is no maximum, because there is only one space of size 1. It's just built on one eigenvector. That's Okay, so now we have this theorem and this theorem, but before we would be able to apply it to discrete wave problem, we should show how to deal with generalized eigenvalue problem. So, what is a generalized eigenvalue? Problem like this. So, we will ask for a couple additional properties. One additional property is this thing should be Hermitian. Do you know, India, what does it mean to be Hermitian?
Didn't you say it's got some values equals to Rayleigh can be ordered?
No, that's a consequence of this property.
Okay.
But what do we say? Okay, matrix A is Hermitian. Is A is equal to A cross, which is this thing. So we first conjugate it and then transpose. And for B, we also want it to be positively defined. Which means so we build a cis-bilinear form, and this form is like a positive number for any x. You understand? So this is just a scalar value. This thing. Yeah?
Yeah.
Makes sense. Okay. It's just the requirements for all that I say afterwards to be true. If it's not true, we cannot do the things I say. So, like naive approach would have been to multiply with the inverse b both sides and get something like this. This is of course a normal eigenvalue problem, but this thing is not Hermitian. And we cannot use Rayleigh quotient right away. So we cannot apply Rayleigh inequality to this eigenvalue problem. Instead, you need to do something more smart. And this more smart was done by Rayleigh. That's how his name is spelled. Rayleigh decomposition. And he proved if we have a positively defined Hermitian matrix, we can present it as a product of two matrices. One of them is lower triangle and of course when we take Hermitian conjugation we get upper triangular matrix. Upper triangle. Okay, I will just to be sure. I will write it down like this. Also, it's upper triangular and all values on main diagonal are positive real, which is also super cool. And we have something here. But above the main diagonal we have only 0. And this thing is positive real. And then you can probably guess. We use this decomposition, and then we do some change of values. So our new problem like this. Then I introduce a new variable y like this, and a new matrix like this. Direct check shows that this matrix is Hermitian. So we have a problem A y A is theta. So what we did, we reduced. So how the Rayleigh quotient changes? Of course, we don't care about this decomposition. It's a technical thing for us. We want the inequality for this problem. So for this problem, what we will get is the following thing. Let me write it down. So this is a slight generalization of Rayleigh result. Okay. Finally. So this is okay. I just rewrote it back. So I wrote it down for A tilde and then I wrote it back for A tilde anyway. Okay. 0.5. simplification. So for FEM, okay, I should probably repeat the statement. This is an FEM problem. This is stiffness matrix, and this is mass matrix. This should be k square. Eigen frequency. Have you ever seen FEM statement before?
It rings a bell, but I can't remember something.
Okay. But that's fine, you know, this is, for you it should be very clear. So if you consider just a mass and spring analogy for your problem, mass and spring discretization, that's one way to write the problem. Because this matrix describes the springs, and this matrix describes masses. And that's why we will get K. So K related to part describes masses. This is just one way to write these equations. This is like a standard way for numerical analysis, and you do it slightly differently. But anyway, that's like an eigenvalue matrix problem. Now I may not rewrite it because I can just put it here. So here I will have, this is K, I just will put the notations for each element. So this is the inequality for FEM. I just changed A and B to K and M. I know it's too simple, but my idea was to write it as many times as I can so you can just get used to it. Because maybe when you see it for the first time, it doesn't seem comfortable. Okay, fine. We have our solution for discrete problem. I will later give some examples, but finally let's talk how to build or how to actually guess. I won't be giving also any proofs, but I will just from this form I already can guess how the inequality will look for continuous problem. Because the continuous problem is actually when we suppose that K and M are infinitely big matrices. There is one approach to wave problem is actually to show that Laplace operator is equivalent to a matrix of infinite size. And this idea can be formalized. And of course I won't be doing that because it's painful. But we can guess. We can do some guessing. So 0.6. 0.6. So, for continuous problem, our eigenvalue problem is written like this. And the following things. Just write them down and then we will discuss. They follow from FEM approach. So let's comment a bit. So you have just a mass matrix, it's just weighting of your, if you just compute a sum of all masses, you will get some like norm of your, like square norm of your function. That should look believable. And for stiffness matrix comes from differentiation. So it's like a discrete approximation of the gradient of Laplace operator. And this thing is like Laplace operator. It comes from Laplace operator after we do integration by parts. And that's a valid guess for the first eigenvalue. It's like this. Okay. And here we have some space of functions. So this U, it's not necessarily a solution of Dirichlet's equation, because if we have a solution, we actually already did everything we want. So this U is a test function. So this function, to be able just to compute this thing, this function should be at least like continuous and have the first derivatives almost everywhere. If it doesn't have first derivative of infinite number of points, it's actually fine. So you can have a piecewise linear functions, they work fine. So you can have jumps of derivatives, but finite ones. And of course, if we were smart people, we would probably said that this is aka H1 Sobolev space. You probably heard somewhere people saying this solution belongs to Sobolev space. So that's what people mean. It should be continuous and have first derivatives. That's, of course, that's very rough, and when you formalize it, things become more involved. And okay, for completeness, for other eigenvalues, we have a similar expression. And probably I should have mentioned again, omega is domain of the whole resonator. So we integrate across whole resonator. So not going into proofs today for this theorem, but what can we do? Like, again, the main step of the proof is to introduce, so we have a Laplace operator and we need to introduce a basis. So if we have a basis Dirichlet, and then we were able to prove that this basis is orthogonal. Then that's basically it. We again can expand our function as a sum of basis functions and use similar estimates we used for discrete problem. But of course we need to be able first to prove this part, and this bit requires a bit of function analysis. But that's very believable. We know that all the modes are orthogonal, and for example for our simple rectangular example, we just can see it's just sinusoidal functions, they are orthogonal. But this thing can be made quite general, and this is true for a big range of cases. Okay. It seems I'm finishing. Oh, I'm finishing content. Example. I will give you one example today. This example is a bit boring, but next time, if you come, I will give a very, very nice example of application of this inequality, which gives you just some new physical knowledge that's hard to find any other way. So here it's hard to see how this thing is useful apart from numerical analysis, but it actually contains some positive information inside. So example is an estimate for first eigenvalue of triangle. So what's the geometry of our problem? Can you see the triangle? The sides 1, 1, 1. And so this is our omega inside, and this is our bound. And this, of course, equilateral triangle edges. My drawing is just ugly. We have the following problem. So let's use the Rayleigh quotient to get some estimate for the first eigenvalue. So the simplest choice, let's take piecewise linear test function. first linear test function. Okay, first let me so we have our triangle and we have so let's take a piecewise linear function such that it's in its center of mass. And then, since this test function should satisfy Dirichlet boundary conditions, this function decays towards the edges. If you're building FEM, this is like the simplest and obvious choice for test function. To approximate the field, so we kind of approximate our field by like some nodal value here, and then we by default satisfy boundary conditions. And if I draw it, from the side view, so this is kind of top view. Let me try to make a side view is like we have, a pyramid like this. Is it okay? And I actually was not lazy and computed this function. So let's put our system of coordinates here 0. So this is 1, 0, and this point is 1 over 2 square root of 3 over 2. Also computed the coordinates of so-called barycenter or center of mass. 6. So our test function can be written analytically like this. So it's just 3 planes and they all intersect somewhere, and then I jump from one plane on another depending on the domain. So it's like this. So what do we need to compute? I probably, I will skip the computation, but we, for example, can take only this area, everything is symmetrical, we can take the smaller triangle and I integrate this function of this triangle, like a double integral. And when we do it carefully, we get the following analytic result. So here everything can be done by hands, and I did it by hands. And for gradient, it's even simpler because this thing is constant. Everything is constant. Just a constant vector, and then I just compute an area, like a third of area, and then also multiply it by 3. After I do it, I get this thing. And my estimate then is this first eigenvalue is less than which is 72. And as Gabriel asked before, what's the accuracy? The accuracy is that we can actually solve this problem analytically. And if we do it, we will find that the real eigenvalue is 4 pi. I think I forgot something here. It's 4. Yeah, because it's and still doesn't give enough. Okay, this I will check and upload the correct. But anyway, when you compute the square, it's 52 of the real eigenvalue, and this is 72. So it's of the same order, but it's kind of makes sense. So it's just we build a finite element method just from one finite element. Still works well. And probably the last comment I will give you today is, do you actually know how to solve this problem? Have you ever stumbled upon such a problem? Yeah, analytically. How to find
I've seen diffraction of the right angle triangle, not equal actually.
yeah, but if you're serious, you probably haven't seen any like proper analytics. But for this problem, if you stay inside, you can yeah, you control. And that's actually not a simple thing to understand, come up yourself. But probably you can guess that if you consider 6 waves, 6 plane waves like this, and you then guess the coefficients of these waves, you will get a solution. So it's the first eigenmode is a combination of 6 plane waves which orthogonal to each of the sides of triangle. I mean, it kind of makes sense because of method of reflection. So you can apply method of reflection to one side, and then after you apply it like 60 degrees, like 6 times, you will get a closed Sommerfeld surface. So you can reformulate this problem on a Sommerfeld surface. It will be quite, you know, like ugly, not ugly, but you will have many sheets, but all these sheets they will close because the angle is p over 6, p over 3. So the angle is p over 3 because angle p over pi over 3. And then once you did it, you can then build the solution on Sommerfeld surface and then symmetrize back. So that's a question of symmetrization. But also coefficients are not trivial. Okay, that's all I wanted to talk today. And next week I will give, as I said, a much nicer example, more entertaining. That's it, and we will continue then with homogenization. Let's see how it goes. Okay, thank you for your attention. Hit like, hit the bell and subscribe. See you next time.